5, 0, right? And then if you look at the symmetry, the imaginary symmetry here, you can see these two numbers. They are the same, but one is the negative of the other, right? Then let's look at another example, 3 by 3. Maybe 0, 2, minus 7, minus 2, 0, 3, 7, minus 3, 0. Then we draw the imaginary again. You see something? These two numbers are the same, but one is the negative of the other. Even this one's 7 and 7, they're the same. The other is a negative of the other, and then the 3. And then, but the most important thing here is these two properties. Should I write it here? Maybe I should put it on the other page. Symmetric. Should be there. And then skew symmetric. Let me just put it here. Skew symmetric. This is probably the most important definition of a symmetry, of a symmetric matrix. Where's this definition? Let me just look at it. Yeah, there it is. Oh man. I have it in my head, but I just want to make sure that it is the right thing. Basically, a symmetric matrix, let's say you have a matrix A. You have a matrix A. It has to be a square matrix, of course. Right? This matrix is symmetric if and only if AT, the transpose of this matrix, if you take a transpose of this matrix, you're gonna get an A, right? And then the same thing this side. The same thing this side. You will have a matrix. It has to be a square matrix, otherwise you cannot talk of symmetry when there's, I mean, you cannot draw a symmetry when there's no diagonal, because the only matrix that has a diagonal is a square matrix. The same thing this side. You take this matrix, you transpose it. This side, you're gonna get a -1. That's how you can tell that this matrix is a square matrix. For example, let's go back to this our example here. If you transpose, if I were to take a transpose of this matrix, right? T, what am I gonna get? Let's see if this rule is true. Transpose, I'm taking the columns, the rows. This row I'm making it a column, so 15, 1. Then I come to the second row, I make it a column, 1 minus 3. You see, it's the same thing, right? Sorry. It's the same thing. And then if I do the same thing this side, I take the transpose, it's gonna be 0 here. And it's gonna be -5 here, right? Then I take the 5, 0 and make it a column, 5, 0. And this is the same thing as, I'm just gonna take a negative, factor out a negative. Is the same thing as -5, 5, 0. Right, you see? If this is my A, let me just put it here. If this is my A, and then I take a transpose of this A, I get A this side, right? If this is my A, right, I take a transpose. What do I get? I get an A, because this is A, you see? I get an A with a negative. So this rule applies. So basically that's it with symmetric symmetric and skew matrices. That's all you need. You just need these two rules. These rules are very important, this one. And we can just start doing the questions today. I'm just going to start with questions pertaining to symmetric matrices, and then we can go and do, because I think I have about 20 questions, and do questions from the previous lesson. So yeah, let's start with the first one. Do you have any questions? Let's go back. Do you have any questions on this? Maybe you didn't understand something, because I might be rushing.
No, no.
Okay, let's continue with questions, and maybe you'll have some questions if we do pass the previous question. Let me just get onto my Telegram, because I want you to see these questions. Let me just share. For example, can you see this one? You can see this one, right? Hello?
Yeah.
Yeah. Since find the value of x, the value of x, y, and z such that the matrix below is skew symmetric. Oh man. Why can't I have the pen? Oh man, let me just change the screen, because this is giving me problems. So we have this matrix. It's like this: 0, x, 3, 2, y, minus 1, equal z, equal 1, equal 0. We are given that this is skew symmetric. Now we need to find x, y, and z, right? Can someone answer it? It's very simple. Let's just get x. You don't have to calculate it. You just need to write it down. Lungi, what is x? Remember, it's skew symmetric. It's skew symmetric.
-2.
Yes, -2. That's correct. And then Nondobeg, y What will be y in this case?
Well, y is in the center, so I don't know. It could be any real number essentially, because it's not affected,
Okay, so you can just
because
put
it's
any
on the
number.
symmetry line.
Yeah, that's true. You can just put any number, right? Yeah, you're right. You're right. And then z will be the negative of x. So in this case, it will be 2. So that was easy. But then there's another one he likes asking. I think there's this one.
Sorry, how is it 2? Because it's at the bottom. Isn't it supposed to be a -3?
Oh, sorry. Yeah, thank you. It means we are you're concentrating. I mistaken this thing with this that. So z must be, because there is a symmetry. Maybe I should draw the symmetry here. This goes with this, and then this goes with this goes with that. So it must be -3, right? -3.
Yeah.
And then another one, it says, given A is a square matrix. Is a square matrix, right? Prove that A, this one is very important. You must concentrate on this one because he likes asking such questions. A plus AT. I saw it there. I'll just show you one he showed in the previous exam, the one that we wrote in December. It's almost along this line. So you must prove that this is this AN asymmetric. You need to prove. You need to prove that this and this is symmetric, right? And remember that the rule says the rule for symmetry is AT is equal to A, right? So we're gonna start with this one. We are given that A is a square matrix. It must be a square matrix, so that's good. You need to prove that this is symmetric. Basically, whatever we're given, this is what we're given, right? This is what we're given. We want to prove that this is symmetric. In other words, we want to prove that when we take, imagine this whole thing being one letter A. When we take this whole thing and then we put a transpose here, what should we get? We should get something that doesn't have an basically
Same thing.
yeah, we should get this, right? We should get AT. This is what we need to prove, but you can't just say this and then this. You have to show some steps, right? So I'm just gonna erase this. Yesterday, remember those rules that I showed you that when you have K, A, then T, we have K, A, T. And then when we have A plus B, T, then it is AT plus BT. Then the other one was A, B, then T, and I said it was B, T, A, T. I said the B comes on the other side, sorry. Comes on the like here it was the second letter. So here it's gonna be the first letter. and then I just remove the brackets. So here is the same thing. We're just gonna exchange these letters. Imagine this being a different letter to this, right? So it's gonna be A, T, right? And then I put a T. Then I take this one, which was first, it's gonna be second, right? And then I forgot to show you this one, but maybe you know it. This one will be A, right?
Yes.
So here will be A, and then AT. So we have proved, right? Good. Anyone confused? Well, we can just move on. The same thing with this one. Our goal is to get A plus AT, right? But we need to show some steps. So using this one, this rule, this is going to be AT plus AT T, which is equal to AT plus A, right? But because this is addition, right? You can just move the matrices around, right? Like this, A plus AT, which is what we wanted to prove. But you must be careful. It just reminded me of something. You must be careful with this when you're multiplying matrices. I'm just going to show you an example. He asked it in the exam with this one. It's probably going to put it again. Imagine you've got two matrices, A and B. And then you have a square. Normally, when you have, let's say we have A being a number, not a matrix, plus B squared, right? Normally, we would say this is equal to A squared. Let me just do it this. Let me just do it like this.
Just do AB plus.
Sorry? You know it, right?
Yeah.
Basically, it's like two brackets here. I'm gonna do it like this. Okay, basically it's the same as A plus B, right? So this is like A squared, AB, and then BA, right? Plus B squared. And then we will say that this is like the same thing. We'll say A squared plus 2AB plus B squared. This is correct when it comes to numbers. But when it comes to, why is it correct? Because we view this as the same thing as AB. Because it's just numbers. 2 times 3 is the same as 3 times 2. But when it comes to matrices, this becomes AB plus BA plus B squared. And that's your answer. You don't add, you can't say it's 2AB, because if you have a matrix A and B and you multiply them like this, you're going to get a different answer to when you have B on the other side and A on the other side. Only when you're multiplying, but when you're adding, you can just move things around. And then there's the one he showed. Yeah, this is the one he showed. There's two, maybe you might show, I'm just going to show you two versions of this. He showed one with symmetric. I'm going to show you both of them. It says prove that if if A is a square matrix, right? Is a square matrix. Prove that A plus AT. Oh, we just proved this one, right? I think we just proved it. Yeah, we've just proved it. Okay? Prove that A minus AT. Oh, it should be easy, right? It should be easy. Yeah. So halfway through, prove that this one is if A, then prove that if A is a square matrix, is skew symmetric. Is always skew symmetric. Right. Or so we can just prove. We want to show that this is skew symmetric, right? So we need this rule. If whatever matrix we're given and we transpose it and we get negative of whatever that matrix is, then it means that matrix is skew symmetric. So in this case, this is the matrix we've been given, the whole of this thing. Because remember, if you had a matrix here, the matrix that has numbers, this whole thing would be like one matrix. So we just pretend it as if it's one matrix. We transpose it, and basically the answer we should get should be the negative of this, which is the negative of A minus AT, right? This is what we want, which can be written as AT minus A. It's the same thing, or minus A plus AT. Basically looking for something like this. We can always vector out a negative. So this is what we do. Using the rules, it's going to be AT, right? Minus AT, which is AT minus A, right? But we're looking for this. So what can we do? We can just factor out negative. We factor out negative. This will be negative AT. And this will be plus A. Then we can move things around. A minus AT, which is what we wanted. Imagine this whole thing. Imagine this whole thing being some letter. This whole thing. Imagine it being some letter B. That means BT in this case is minus. So yeah, I think we're done with symmetric matrices. We will move on to the previous lessons. We'll be doing questions today. Does anyone have any question regarding this?
Okay, there was a question on the exam last day. I'm not sure I have it. Do you have that paper?
Last year.
Yeah.
Someone, I think someone gave me some of these questions. Let me just look at here. Was it on matrices?
Yeah.
But I think we've just
Based
done
on
it.
this.
We've just done it. It's just that maybe now you can see. Yeah, there it is. Let me just share my screen. We did it, man. We've just done it, man. It's just that maybe this one.
Yeah, this one.
Yeah. Can you please yeah, can you mute yourself better there so that because we can hear the kid there. Okay, I'm just gonna mute you. Okay, I've just muted you. Hey, anyways, I think she's gone. But yeah, was she the one asking this question?
Yeah. No, I was the one who's asking.
Oh,
this
okay. It
question.
says let A be a square matrix. Which of the following statement is true, right?
Yes.
It says this is symmetric, it's skew symmetric. And then it says this whole thing is skew symmetric. And then it also says this is skew symmetric. And then it says this is skew symmetric. Can I just write it down so that I don't know, man, if I can. I can't edit here, so we need to go back to the whiteboard. Let me just write it. Quickly jot it down.
You're sleeping. Don't get to sleep. But decided to work.
A minus AT, A plus AT, then AT, and then A minus AT. All of them skew symmetric, right? And then more options. Great. I'm switching on to damn. What 6 minutes before this thing? Let's see if we can do it. I'm sure we can finish this one. Right. So the first one, basically we need to find out if this A minus AT T. We need to find out if this thing is skew symmetric. This whole thing, just imagine this whole thing as being one letter. Maybe we can say this is B, right? So basically the question is asking us if, in another way of thinking about this question, is asking us if B is skew symmetric. Basically, if we take the transpose of B, are we gonna get minus B, right? If we do get minus B, that means this statement is true. But let's find out if it is the case. A minus AT, right? T, then T. Because this thing is like one thing, right? But I'm just gonna do step by step. I'm gonna distribute this one first. It's gonna be AT minus AT T all to the power T. Then this will be AT minus A all to the power T. Then I distribute the one outside. It's gonna be A T T minus A T, which is equal to A minus A T. Right? When you look at this, that negative B would be something like this. A minus A T T, right? Which is the same as negative AT minus A, right? This, yeah. when you look at this, does it look like this? Or can we, another way of writing it would be A ST plus A. When you look at this, does this look like this? It does, ne?
Yeah, it does.
Exactly. So basically, you need to understand what we're looking for. In this case, this whole thing, that's what the question said. This whole thing is skew symmetric. So we needed to find out if this thing is skew symmetric. And we know in order for something to be skew symmetric, oh wait, sorry. Yeah, it's fine. It looks weird though, because it has so many t's and we are just used to it being by itself, not having another t. It's a check. You just need to know the whole of this thing. And then you put a transpose a t over it. You should get a negative of this whole thing, which is this, right? Negative of this whole thing. And then just play around and simplify it so that you have it in different formats. Because even from here, I could make this thing to be like this. Let me show you real quick. This is the same thing as I would write it like this: t minus a t. Because why? When I distribute the t, I will get an a. When I distribute the t here, I'll get an at. And then and then I could just vector out a negative. This will be let me just put a bigger bracket. This will be minus 80 plus a, and then I put the t. This t is this one here. I'm just factoring out a negative here. If you're to distribute a negative, it becomes 80, and then it becomes negative a, which is equal to, then I can just, it's this rule, this one. K being a constant, any number, t is equal to k at, right? So the same thing, if I distribute this t, right, it's not going to affect the negative, right? I'm just removing the bigger bracket now. And then here I can just switch these things around. Minus at. Then I put the t, which is what we wanted to show. Can we continue? I'm just going to invite you again. I'll put the link. Lungile is going to post it because I don't have access to the Telegram group. So yeah, I'm just going to post another link now.